Yeah, it is recording now. Okay, so yeah, so in probability theory, you should know everything about random variables. By everything, which I mean is discrete random variables, all the related concepts and different kinds of random variables, conditional probabilities, and not only one variable. I mean, not only a single random variable, but random vectors. And you should know conditional random vectors and related concepts and different kinds of distributions. So this is a prerequisite for information theory. If you have read it long time back, then I must suggest you to re-look at it. So just go through it again, because in the beginning I'll recall some definitions and I will not consider what it means. I'll just recall the definition, okay, and I'll not explain, for example, what is the meaning of random variable and why I'm writing some, for example, what is the proof of some result, some small, I mean some, let's say, important but not very non-trivial result I'm using. I'm not going to prove that, okay, because you're supposed to know the proof. You're supposed to know the proof. So that's why I'm saying that you must you must you must go through the probability theory once again. Now, what are the concepts, okay, related to random variables? You must know that, okay, because I'll be using a lot this random variables. And initially, I'll recall the definitions, but after that, I'll not recall any definition. Okay, I'll just use those concepts. And the second part, algebraic coding theory, linear algebra is a prerequisite, and linear algebra is also, I mean, is a very generically very big subject. But so what part is required here is like the rank, the kernel, I mean the null space, the range space, and yeah. So basically, how to compute rank, what is the meaning of rank, linear independence, how many linear independence, and so when do you say a set of vectors linearly independent, linearly dependent, this stuff, this kind of stuff is important. Okay, and secondly is we will not only talk about vector spaces over like over the field of real numbers. We'll also consider vector spaces over a finite field. So, so we always define vector space over a field. So here we'll work with finite field. Okay, finite field meaning like if you like R is a prototype. R means that our real numbers. That's a prototype of a field. Okay, whatever the properties of R you have. So you must have, I mean, if you had a course on linear algebra, you must have, I mean, you must know what is an algebraic field, because we always define vector space over a field. And here in this course, those that field over which a vector space is defined, that field is a finite field, meaning that field contains only finitely many elements. Okay, so and there will terms like polynomials, those will be used like set of all polynomials from also a vector space. Polynomials may be bounded by some degree, degree is bounded by some number, okay, or maybe all polynomials. So this kind of things will be used for algebraic coding theory part. And this course is not about only about these two different topics, but it is also interconnection between these two topics. So if we look at the syllabus, the syllabus is very old. I mean, which you can find in this our IIT KGP web page. So the syllabus is very old, and syllabus only talks about the coding theory part. But here we have both the things, information and coding. And last time means last year, I think. Last year, I I conducted the lectures for information part only. So yeah, so both the topics are here, information and coding. Here the coding, it is not computer programming. Okay, here it is coding means how to code. So if you, so okay, I'll talk about it, but just to give you a brief kind of idea. Here the coding means, for example, suppose you send messages, videos, you share videos using some kind of a device, let's say WhatsApp, or using an email, whatever it is. Okay, so there is a communication system, underlying communication system, or you can say digital communication system, through which you share these things. Now, whenever you are sharing, so computer does not understand what is A, B, C, D, and so on. So computer, the way computer is built, it is like, or the machine is built, whatever machine you are using. So in that machine, so for example, the letter A is represented as a bunch of zero ones, and this bunch of zero ones is again represented by some electronic device in the machine. So then the question is, given a letter or an alphabet, let's say A, capital or small, whatever, okay, A or B, how do you define a bunch of zero ones which can represent A or B or any other letter, whatever symbols you are using when you are sending or writing a message? Okay, because the machine does not understand the English language or any language. Okay, so we have to make it understand. So that means we have to represent this English words or letters, okay, alphabets, using some bunch of zero ones, where the zero ones represent some physical quantity like voltage or current, whatever it is, depending on your architecture of the machine. So whenever we do that, like voltage, high voltage, let's say it is one, low voltage it is, let's say, zero. You have, let's say, yeah, a transistor kind of a thing. So then if you put some of the put, let's say, a finite number of transistors side by side, okay, then that may represent a bunch of zero ones depending on whether the voltage is high or low. So this is kind of a situation. Okay, then the question is, the coding theory means how to code a particular symbol, or let's say you're listening to some song, okay, and the song is, let's say it is in some hard disk, okay, or some movie file you have that is in some hard disk. But the movie file, okay, it is not, it cannot, it has to be stored using a mechanism, right? So the same mechanism here also works. So mechanism is whatever is there, the video file or the audio file, whatever it is there, okay, that has to be converted into bunch of zero ones. Okay, so this conversion, like from something which we can understand, some language, okay, from that making that into a sequence of zero ones, bunch of zero ones, strings of zero ones. It's called the process of coding. Okay, how do you encode this thing? So this is covered, and then how do you decode it? So whenever you download and put it some disk, so this is the encoding process. Something is there which encodes this. There is a rule through which it is encoded. And decoded means whenever you play later on, okay, so that means it decodes the information from the disk, let's say, or whatever hard disk you have. So from that it decodes sort of information you already had. So coding in that sense, like hiding information or coding something, some message, okay, in terms of the machine language, in terms of some bunch of zero ones. Okay, not exactly machine language, that's a different topic, but let's say just in terms of zero ones. So the question will be, how do you decide, okay, what should be a sequence of a string of zero ones for a particular letter or for a particular alphabet, for a particular whatever it is, okay, whatever you want to transmit from one place to other place. So this is what is called the coding. Okay, and information and coding has huge application in all branches of engineering. And information, since we are from chemical, we'll talk about it a little bit. So what is the original idea? Where does it come from? Okay, the information. So this is there in your thermodynamics also. So this is where the idea comes from. So yeah, so in statistical mechanics. So this concept information is heavily used. Okay, so no, so I will talk about it. What is information and this and that. So and so this course will be also. Let me declare this. This course will be highly mathematical. Okay, highly mathematical meaning you have to. I mean, mm, I mean, uh, how do I put it? So don't expect anything which is, let's say, not mathematical, meaning it is not a story kind of a thing. Okay, so you really have to do mathematics here in this course. So I mean, you will see in this course that if you are not acquainted with uh, use of a lot of mathematics, then I would recommend you not to register for the deregister this course, because in this course mathematics will be heavily used. Mathematics, by mathematics I mean probability theory, random variable, and linear algebra. This both the concepts regarding random variables and matrices that will be heavily used here in this course. So if you are not habituated with using a lot of mathematics, then this is a course which is not for you. Okay, so I'm saying this because many students do not know, because the thing is, this name is very fancy, information coding. Okay, so they have different perception about these things, but the way it is done, it is little different. Okay, or at least the way I do it, it is little different. And here, information is actually a mathematical subject. Okay, of course, algebraic coding theory means algebra is there. Okay, whenever I write algebraic, it means coding theory need not be only algebraic; it could be geometric as well. But we'll only focus on algebra part because geometry part is a little advanced. So we'll only focus on the algebraic part. Okay. Now I'll recommend basically three books which you can follow, and gradually I'll also tell you other books. But these are the famous books which I always recommend. So one book is, I mean, I'll first uh, talk about one book, two books on information, which is uh, first one. The title is Elements Elements of Information Theory. Information Theory. This is by Thomas and Thomas. Okay, uh, Thomas and Thomas, and one of these guys is Indian. Thomas and Thomas. And there is another book, which is also a good book. This, I mean, famous book. This is, I mean, if you go through any web page, uh, okay, related to a course on information theory anywhere in the world, one of these books is followed. So these are very standard books. These two books. A first course in information theory. Information theory. This is written by a person from Hong Kong. His name is Raymond Yang. And I would like to suggest you another book where you get both the things like the information and coding theory both. This title of this book is the theory of information, and coding. This is a little old book, but this is a good book. I mean, if you want to get a flavor of real means practical things, then this is what you need. This book. I'll also tell you. I mean, when I say a lot of mathematics is involved, Okay, I'll also tell you why this mathematics is used in order to implement something. Okay, that will also I also will try to explain. But the language is completely mathematics. So yeah, so that is I just want to make a note of it. ECE. Macaulay. Okay. Yeah, RJ Macaulay actually. So yeah, these are the books, three books which I'll recommend you to read, and most of my whatever I'll be discussing will be from these books only. And this book is very very mathematical, by the way. This book, Thomas and Thomas. This book. I mean, it is a mathematics subject on mathematics, of course. All the books are mathematical, but it is much more mathematical. Thomas and Thomas. You can, and these books are available. I mean, you can find it in library Genesis or anywhere. Like you can find it these books online. It's not a problem. If you don't find it, then just let me know. I'll find a way to. I have the soft copies of this book, so I can find a way to give it to you. Yeah, this is the thing, and I have not decided anything about the exams. Okay, so how the exams will be conducted, what will be the grading policy. I have not decided it, but as we go along with the course, so we gradually develop a mechanism. But of course, there will be exams, probably MCQ type questions, multiple choice questions, homework, and you have to submit the homework problems, the solutions of the homework problems, and of course, Viva. These three components will be there. Okay. Yeah, so this is the thing. And what I want to say. Okay, do you have any other question you can ask me now? If you have any other question.
So I'm familiar with probability theory and linear algebra, so like, is it possible for me to continue?
You're familiar means I don't know how much you're familiar with, right? So it's up to
I
you.
have done courses in the math department itself.
Oh, yeah, you are Devojay. Okay, yeah. So I know who. I mean, what are the courses you have done? Okay, for you. Okay, I thought somebody else is asking. You can do it. Yeah, I know you can do it. Yeah, I mean, when I say undergraduate students, not who roll number. I mean, who have already done these courses for them. Like there are some students like whose roll number starts with 19. They also have registered. So
Okay.
then I had to tell them that you please deregister this course because they are doing probability statistics in this semester, so they cannot do this course. And
Okay,
by the
fine.
way, yeah, and for this course, actually, this is a PhD level course. Okay, so yeah, so you have to understand that this will be a little advanced. Okay, I mean, will not define something which you are supposed to do it in undergraduate courses. I mean, we'll recall, I mean, many a times, but some of the things we will not. We'll say like it follows from that fact. Okay, so because we're not to prove that, because if you want to prove that, then it will take a lot of time. So we'll be using some of the results. Okay, which you are supposed to know. Okay, yeah. Yeah. Anything else? Anybody?
Good afternoon, sir.
Yeah, Japanjot. Yeah. Go ahead.
Sir, I did one course on probability theory during my MSc. That will be enough.
I don't know how much you have done this. So, but you need both probability theory and linear algebra.
Sir, like linear algebra, like I did it properly, but I am like little bit confused about probability theory because I have did
Yeah.
only one course that was very basic. Like uh,
Okay. So,
that's a,
okay. So let me ask you a question. Okay. So, what is the random variable? What is random variable? Let's say. What is it?
sir
Do you
random
remember
vari.
anything? Yeah.
Yes, I do. I know what is random variable. So
What is that? What is that?
random random variable is a function basically,
Mm-hmm.
and it is more like uh, it's a function just like if we have If we are like, I'll give an example of random variable that will be more efficient. I don't remember the proper definition, but it, like, if we are tossing a coin, then there are two possible outcomes, so 0 and 1. So here our random variable is taking two values, zeros and 1.
Okay. Anybody else wants to answer this question? What is a random variable?
Yes, sir. Can I say, sir?
Yes, go ahead, go ahead.
Sir, random variable is a function defined from sample space to set of real numbers such that inverse image of Borel set should be belongs to sigma algebra set, which is defined on sample space.
Okay. Anybody else wants wants to say something about what is the random variable?
Sir, for a given sample space S of some experiment, a random variable is basically a rule that associates all the element of a sample space uh, by numbers. That is basically uh, if we give any element of the sample space into the random variable function x, then we will get an input x, which is basically a number.
Okay. Anyone else? Okay, so more or less whatever you said, all of you whosoever said, so more or less it is correct. But you have to understand. So this is just a definition, okay? But you have to understand also what is the logic behind this definition. Why it is defined this way? Why do we need to study random variable? Let's say.
Sir, because
Mhm.
because let's say we have head and tail or things like that, we cannot mathematically use those and make equations out of it. So to actually give this a more mathematical and abstract form, we actually we tend to convert them into the number space. So that is exactly why we need random variables.
Okay. Good. Yeah. So this is not the only reason, but this is one reason. Okay. Or I will say one of the important reasons. Okay, that's fine. This is good. So, okay, by the way, I'm forgetting. So I need to make an announcement. Okay. So are you guys free on Saturday? Saturday, let's say 10 to 12? Because this month, the month of January, I want to actually, I am not in India right now. I am in USA. And here time is now 4 o'clock in the morning. I started at 3:30. Okay, so it is 4 o'clock. And tomorrow class will be like 2:30 in the morning and it will be up to 4:30. So tomorrow class, like the Friday's class, I am to change into Saturday morning, let's say 10 to 12. Is everybody free during that time? Otherwise, I will have it on Friday, no problem. For this month only, because I'll be reaching India by 31st of January. So after that, we'll have, as usual, this same schedule. But is there anybody who is not who is occupied during that time, Saturday 10 to 12? Then we'll convert tomorrow's Friday's class on Saturday only for this month.
Sir, can you take in the evening on weekdays, like from 7 p.m. or 6 p.m. like that?
Mm, evening. Evening I can conduct, but this will be little late because early morning, there is a problem. Problem means I have to take my son to school. That's the problem. Okay, and my time is not fixed when my son will wake up. Time is not fixed. That's the problem. So it little varies. So So that's the problem. I mean, because in India it is evening, means here it is morning. And wherever I'm staying now, it is morning. So otherwise, what we could do is, yeah, Saturday, Sunday evening I'm free. Maybe, yeah, that is I'm free. Saturday, Sunday evening I'm free, but not during
So
the weekdays.
it's better to take in Saturday 10 to 12 only, I guess. Everyone should be free at that time. Like last semester, we used to have extra classes at those points.
Yeah, yeah. So is there anybody who is occupied during that time? Saturday 10 to 12? Because that will be for evening for me on Friday, 9:30 to 11:30. Okay, it seems everybody is free. So let us make this note of it. Saturday 10 to 12. Okay, AM. Okay, 12 is noon, by the way. So let us write 11:55 Saturday. Okay, this will be the timing instead Friday. Only for this month. Okay. So we'll have this tomorrow's class, like Friday's class, on Saturday morning. Yeah, this is one announcement we want to make. Any other questions you have? No, no question. Okay, so now let us start. Okay, now let me. Okay, so we'll start talking about what is called what is information, by the way. And this is a questions
Sir,
which
your
is.
screen is not visible, I think.
Oh, I see. Just a minute. Just a minute. Okay, so what is information? Okay, what is it? What is it? And my simple answer will be, it is hard to answer. I mean, whenever I say what is information, that means in the general context. So, for example, suppose I give you a scenario. Let us say you want to send a fax to somebody else. Okay, a fax, just a fax. So you have a fax machine here. Okay, and you want to send something to somebody else. Something means you want to send a message. Now the question is, so this is a paper, okay, which you want to send. So this is the message you want to send. Now you want to write something here. This is your message. But the question is, what should be the font size of the letters we are using to write this message? One thing is, if you use a very small, the font size very small, then you can use a lot of letters, a lot of alphabets to write the message. And maybe it will reduce the cost also, because since you are using fax machines, okay, so you need to pay something, okay. So you need to pay the proprietor of the machine, let's say, who has this machine, the machine we're using. You need to pay a certain cost, okay, to transmit this message or transmit whatever is there written in that message to somebody else. Okay, this is also, let's say, fax machine. Now, the next thing is, if you want to make the font size too much small, okay, then there will be a problem, because there is a fixed resolution, let's say finite resolution of the fax machine. So if you want to make the font size very, very small, then it may be possible that the receiver of this message, he or she, cannot understand what it is written. Okay, so if you want to optimize the cost, like let's say if you want to make font size 14, let's say, suppose you need 2 pages, but if you make the font size 10 or maybe 8, then you need only 1 page. Okay, so there are two problems now. You want to reduce the font size of your message, okay, of the letter, whatever you are writing, font size of the letter, and in order to reduce the cost. But you also have to see whether the receiver, okay, whosoever the receiver is, whether he or she understands whatever your message is, or she can read, he or she can read your message or not. That is also a problem. So you have to optimize. So you want to optimize the cost, okay, to minimize the cost, provided that the receiver understands the message. Now it may so happen that you once understand or you can read that 8 font letter, okay, but the receiver can read, let's say, some of the letters, but not all the letters, but the receiver can understand what you meant in that message because the receiver understands the context. Okay, that may also can happen. I mean, some of the letters maybe the receiver does not understand, but from the context, the receiver can retrieve the missing letters. I mean, what are the letters which the receiver cannot read, but he or she can make a guess about those letters, and he can retrieve the message. Okay, that also can happen. Then the question is, if I ask you, what is the information in this message? Okay, that depends on many scenarios now. One is what is the context? Because if the context is not clear to the receiver, okay, even if only few letters are missing, like only few letters the receiver could not understand, he or she may not understand what is written, what is the information in the entire message. Okay, the receiver may not understand anything. On the other hand, if the context is known to the receiver, then even if some of the letters are missing from the message, a receiver can retrieve what the information is in the message. So now if I want to define what is the content of information, what is the quantity of information for this given message, okay, that's why it is very hard, because it depends on many contexts. Okay, this is my first example. My second example, why, I mean, because I asked the question that what is information, and I said it is hard to answer. Okay, and I'm trying to tell you why it is hard to answer, that how to quantify what is information in a message. This is my first example. My second example, let's say you are listening to a music. Okay, you are listening to a music or maybe a song. Okay, let's say it is sung by A.R. Rahman. Okay, so you are listening to the song. First time you listen, you likes it. Second time you listen, you like it, or maybe you will like it more, and so on. Now, if I ask you, suppose you listen to it 100 times. Now, if I ask you, the first time when you listen to this song, what was the amount of information in the song? Means what was the message it was carrying? Whatever you have understood. And after playing it 100 times, okay, what do you understand about the music or about the song or about the lyric, whatever it is? So then you will see your answer will change after listening to it 100 times and after listening to it just for the first time, or maybe at the 10th time. Okay. So but you see, information was fixed in the song, whatever information it was carrying, that was fixed. But since you possess that information multiple number of times, okay, you possess more information out of the same message or same lyric or same song or whatever the music, same music. So if I want to just define in a single line, what is the amount of information in a song or in a lyric of a song, okay, or in a music, it is very hard to define. Okay, so that's why I said it is hard to define. So if you want to define information in a generic context, like what is the information in a message, what is the information in something, okay, in any ABCD things, that could be very hard to define. Okay, so I mean, it is always hard to define. You can understand why it is using these two examples. Okay, by the way, if you have any question anytime, you can always ask me. Okay, no problem. Now, now the question is, but we want to process information, right? So process information is, suppose I have some information, I have a message, okay, which I want to send you. So let us go back to the world, okay, around 1900, let's say, okay. So then you do not have mobile, you do not have laptop, you do not have these machines, okay, sophisticated machines, okay. You do not have telephone also properly working, okay, let's say. Then the question is, and then in the First World War, then the Second World War, okay, in the Second World War specifically, okay, so there are two allies, let's say, and one ally, let's say, is sending some information to his colleagues, okay, and then another ally, they want to know what is that information. They have to somehow crack the information or hack the information in some sense. So then they have to understand. So they are that time in sending information or sending messages means in terms of radio, okay. In terms of radio, so if they somehow catch the frequency, the other party, opponent party, if they somehow get an idea about the frequency, then they can crack what is the information, okay. So the question is now, whenever you are sending information, you are sending through an unreliable channel, because there is always a a chance of leaking of information, okay. For example, you are sending me message, okay, there is a chance somebody can hack your machine, somebody can get to your password, okay, in a modern context. So in today's context, let's say, so there is always a possibility that the medium using which you are sending a message, okay, that is not reliable. I mean, you can assume that that is unreliable, okay. Whether it is reliable, because nothing is reliable in the world, because everything which is artificial, you cannot say it is reliable, okay, because somebody has made it, okay, including whether it is a voting machine, whether it is any kind of machine, okay, it is not reliable because somebody has made it, okay. That's why it is artificial, it is not natural, so it is unreliable. So the question is, you want to send the information, okay, through a channel, that means through a medium, okay. I will define what is a channel, because we will be using this word most frequently, channel. So using a channel, you are sending a message. That channel is unreliable because there is a notion of noise, or there can be eavesdropper who can hack your message and so on. But you want to have a reliable communication. So how much information? So for example, you want to send me a message, okay? Then you can encode the message. You can do something with the message so that I can understand. But suppose somebody hacks the information, he or she cannot understand unless he or she is intelligent. Let's say intelligent is something, let's say, which is abstract term. Okay, so the question is, how do you reliably send information through an unreliable is through an unreliable channel? So that is the job. Okay, now in around 1948, just after the Second World War, around 1948, there was a guy called his name is Shannon. Okay, he is known as father of information theory. So Claude Shannon, Claude, Claude E. Shannon. Shannon. So he physically lived in this world around 1916 to I think 2001. I have a little doubt, but I think 2001. So this guy, around 1948, he published a paper. Okay, uh, published a scientific paper. At that time, he was working in Bell Telephone Laboratory. By profession, he was an electrical engineer. So he published a paper or an article, you can say, but in academic world we call it paper. Paper title was title was, I think, the mathematical mathematical theory of communication. This is the paper he published. Okay, and it is, I mean, it laid the foundation, okay, of the entire field information theory. So whatever we are doing today, we are sending information, it is due to this paper only. The main concept started from this paper. And when this first time this paper was published, mathematician could not understand what is the mathematics involved here. Electrical engineers, they also did not understand what is communication involved here. Nobody could understood first 2 years of the publish of this paper. So this paper was so intricate. This paper was so advanced. So nobody understood what it is actually. What is the content of this paper? What is the meaning of his ideas? Okay, nobody could grasp that. So we will build up the concept which will help us to understand what he meant by saying the theory of the mathematical theory of communication. Okay, what is it? Okay, so he idealized a digital communication system, which is very vague, or maybe which is, let's say, very standard, and then you can have some advanced features of it. So he considered this as a prototype of a digital communication system. Okay, this is where from you want to send in some information. So I did not define what is information, by the way. I only said information is something which is hard to define. If you ask me what is information, I'll say it is hard to answer, but we'll try to understand what it is. Okay, and we'll formally define according to Shannon what he meant by information. Okay, so yeah, so his idea of information was in the context of digital communication system. Okay, not in a generic sense, like what is the information in a message or what is the information in a song. This is what he did not define. Okay, information. He defined information in the context of a digital communication system. So, so his system was like this. There is a source of information. We'll define everything later on. See source. So here something, a message is generated. Let's say a message is generated. Then there is a transmitter which will transmit the message. Transmitter, and this will send some signal using some signal. If you do not know what is a signal, you may just assume, if we just read any the first chapter of any book on digital communication, or otherwise you can assume a signal means kind of a function. Okay, where there is a, let's say it is a digital, I mean there are two kinds of signal, one is analog, one is digital. So, or maybe in some music player, you can see what is the signal. In some music player, where you see that there is, if you increase the volume, something, some frequency kind of thing, some function will be like sine curve like functions. Okay, so whenever it is like taking a high value, it is one, and now this low value means it is kind of a zero. So basically, it is a sequence of 0 1 in the sense of a digital signal. For the analog signal, it is just kind of a function. You can have like sine and cos kind of a function, because any function can be approximated using a series of sine and cos, which is called a Fourier series. Okay, so signal means it is kind of a function where there are some high value and there's some low value, and high value is something like 1 and low value is something like 0. You may assume like that, or otherwise just read first chapter of any book on digital communication. Okay, so then it will transmit into some signal, then this will pass through some channel. So there is a noise. Noises, for example, if I shout from here, like suppose you are standing 100 meters away, okay, from me, and if I shout, okay, if I call by your name, you may not hear me because there is a medium which is wind, let's say. Okay, so you may not hear me because there is some medium, okay, which is a noise. Due to that, if I'm not louder enough, you may not hear me, you may not know, like I was calling your name. But if I am too much louder, then maybe we can hear my name. So there is an amount of noise. I mean, depending on whether it is like the environment is very quiet, or like if you are shouting in a street in Calcutta, you will never going to hear if even if you are 100 meter away. How much loud you ask, how much loud you say. So depending on the this noise, okay, because noise means it is of different kinds of sounds are there. Let's say that's an example. So whatever the medium is, so there will be some kinds of noise through which this signal will pass, and there is the received signal here. Received signal. Received signal. So this is received signal here. This is the receiver, and then the message is retrieved, and this is the destination. So this is message. This is the destination. So this is broadly, this is the idea of a digital communication system. And this is a point-to-point digital communication, meaning some source, there is a source and there is a destination. Okay, there is a source and there is a destination. So it's a very point-to-point communication system. Now, in this kind of a communication system, and now you can assume, let's say this information source could be anything from anywhere you want to send something, okay, some message you want to send. And then it has to process through something, through some machine, okay, and then it has to go through satellite communication, whatever the medium is, okay, and there will be some kind of noise, of course, and then somebody will receive the information, okay, receive the signal, and it will retrieve, it will decode what is the meaning of that signal, it will retrieve the message corresponding to that signal. The best example is if you're watching a football World Cup, okay, suppose it is held in some place in Europe, and you can see or you can watch the game, the match, okay, sitting in your house, and a lot of this entire communication system is just an example of that. So some signal is being sent from there at that place, and there is some communication system through satellite communication, whatever it is. There is some antenna which will catch the signal, and then it will retrieve the video, and you can watch it sitting at your home. So this is just like a point-to-point communication system. Okay. Now, in such a context and such a scenario, like for a point-to-point digital communication system, Shannon introduced two fundamental concepts, I would say, about information. And what are those concepts? I'll tell you those concepts. So Shannon introduced two concepts. Okay. First concept he gave about information. He said you should write his paper. You should read his paper. You may not understand it, but at least go through his paper. Okay, this paper, which I said, the mathematical theory of communication. Okay, this is available freely. Just type it in Google. Okay, you'll get the paper. Just go through once. Okay, you'll see the beauty of the paper. So he just said this, that information is uncertainty. Information is uncertainty. I'm just quoting him. Okay, information is uncertainty. Okay, this is what he said. Now, what it means basically, okay, information is uncertainty. So that means it probably says, like, if you have a message, I mean, let me bring that in the context of a message because this is where I started. So probably it says in a message, okay, how much, what in the message is conveying something to you, okay, about some event or something. Okay, now here how the probability will come, you will see. So it is some kind of, it is talking about some kind of event, let's say. Then the question is, if the event, okay, is much uncertain, meaning less likely to happen, that means probability of that event is very, very small, close to zero. That means it has a lot of information. So information is uncertainty, meaning if there is anything which is certain, there is no information. So there will be information if something is uncertain. And if you increase the level of uncertainty, probably, so it will contain much more information. This is what he meant. We'll explain all these things later on. I'm just telling you the story. Okay. So he said information is uncertainty. And what he basically meant is if something is certain, there is no information. For example, if I tell you tomorrow the sun will rise from east, okay, this is a message I'm sending it to you. You will not be surprised, okay, because there's nothing certain and there's nothing uncertain about it. You know that it will rise from east. That is fine. But if I say that tomorrow the sun will rise from west, because then what is suppose you believe that information or I believe that message, then this is surprising. Okay, so this is something which is uncertain. Okay, this is not certain, so it carries some amount of information. So anything which is certain, let's say there is no information, but information will only be there if something is uncertain. Then the question is, how do you model the information source? Okay, so because we are talking about uncertainty, then there must be, how do you say, must be something which will measure how much uncertain is, or how much uncertain an event is. Okay, so an information source, an information source, he he modeled it like this: an information source, or see, information source is model according to him. This is model, or it should be modeled as a random variable. Okay, a random variable, or let's say a random process, whatever way you know it. Okay. Okay, so this is how he defined it. So an information source is modeled as a random variable and random process. And the probability theory is of course used to define the information, okay, of the amount of information of the random corresponding random variable. Okay, how much uncertain a random variable is. For example, if I ask you, I think Papunjot gave that example that if we toss a coin, either head or tail will appear, and we can define a random variable. Let's say for head it is 0, for tail it is 1. Then if that is the random variable, then the question is how much uncertain this random variable is. So first of all, we have to define what is the probability of all the outcomes, because random variable, if you want to say what is a random variable, then this random variable is associated with the probability space. Okay, so we first need to, so whenever we define something called a random variable, first of all we need to decide what is the probability space. That means what is the sample space, what is the possible set of events, or somebody said about sigma algebra. So what is the set of possible events, and what is our probability measure? If I know all these things, and then I define what is a random variable, or I know the probability of values of these random variables, then I can accordingly say what is my sample space and what is my probability distribution, what is my probability mass function. Okay, if it is a discrete random. By the way, so here most of the time we'll only consider discrete random space, discrete probability space. I mean discrete sample space. Okay, our random variable will be discrete, where the sample space is countable. Okay, as a set it is a countable set. By countable I mean it is either finite or countable infinite. Yeah, so the basic idea of Shannon was there are two ideas. So he said information is uncertainty, and it is hard to believe what he meant first time. Okay, what is it? We'll talk about it. And second thing which he said, uh, he said information which is to be, let's say, which is to be transmitted, okay, it has to be transmitted, has to be digital. What does it mean? What does it mean? It means, see, first of all, he said what is an information source. He said information source is a random variable. I mean, can be modeled as a random variable, let's say. Now he's saying that it has to be transmitted, okay? Information, if you want to transmit an information, it has to be digital. It means that information source should be converted into streams of some strings of, let's say, 0 and 1s, okay? And I mean, 0 and 1 means, these are called bits, okay? Binary digits, okay? That's why 0 and 1, okay? As I said before, I think you know this basic. So yeah, so 0 and 1, all these things, okay? So digitally means, by digital, what he meant is, I think in the previous course, I mean, in last semester course, the MTech students, we talked about this, digital, and we talked about bits also, 0 and 1. So by this, what he meant is that this information source, let's say the information source, okay, this should be, okay, let me first give you an example, okay? Now, let me first give you an example. Suppose I have a message, okay? You want to write a message, okay? Now, in this message, you are using some alphabets or letters, okay? But if you write a letter, okay, I write a word, let's say, these words, any word consists of some letters, okay? Now, in the entire English dictionary, you know how many words are there, and you know each of these words, what are those letters, I mean, which will constitute those words. So I can define probably a random variable, okay, where the sample space is all the letters, let's say A to Z, okay, let us say all are small letters or capital letters, okay, A to Z, and I'll define the probability of the letter A, let's say, is number of words which contain the alphabet A divided by total number of words in the dictionary. So what I'm trying to tell you is, whenever you write a message, the letters which you use to write the message do not come randomly. It follows a distribution. And you can check out in Google, okay, just give it a search, that what is the distribution of the alphabets, okay, in a dictionary, means number of the probability. You can define what is the frequently used letters, let's say, in all possible words in English language, okay, or in the English dictionary, okay, let's say, and then you'll see A, S. These letters are very, very frequently used compared to, let's say, Z. Z is a letter, like Z. Z is a letter or alphabet which is not frequently used. Okay, so the probability of having Z will be very, very less. So then the thing is, so information source in that sense, whenever you are saying, see, you want to write a message. Now, how you come up with the random variable? You come up with a random variable because these letters which you'll be using to write the message do not come every letter does not come with equal probability. Okay, so some letters are highly probable, some letters are less probable. So there is a random variable already inbuilt inside your information source. Okay, if you consider information source is something, or let's say it is you who is writing a message or who is writing a letter, okay, who is writing a message using, let's say, some language, English language, let's say. So there is already an information source okay, which is responsible for the use of the alphabets which you'll be using in the message. So all the letters are not coming randomly. Okay, there is some letters are most probable, some letters are less probable. Okay, yeah. So whenever he said digital, he meant that you have an information source, and that source now has to be transmitted in terms of something digital, which is in terms of 0 1. Now, in the context, in the context of the message, and this is very crucial. This is where this coding theory will appear. Okay, in the context of the message, let us say if I have a letter which is highly probable, that means it will I will have to use that letter most frequently. Then what I'll do is I'll use a very small length or more a very a string of 0 1s of very small length, let's say 0 0 1, something like that, or I'll just use 0, or let's say 0 0 2, 0 1 0, something like that. A sequence, I mean, a sequence of 0 1s, which is of small length. And if there is any letter whose probability is less, I mean, that will not occur very frequently. Maybe in the entire message there is no letter, there is no word which contains the letter Z, let's say, for example. Then I'll try to use a very high length sequence of 0 1, a string of 0 1, in order to identify that particular letter which seldom occur, or whose occurrence is very less in terms of probability. Okay, the probability, the way I define the probability. So then what is happening, this coding theory, it is involved here. Okay, coding theory means how do you generate these strings of 0 1, and that depends on your information source, which is the probability, the random variable. Okay, so whenever you are sending a message, okay, you want to send a message means you want to send a bunch of letters. Now you have to digitalize this, meaning whenever you are using the message, writing the message, this A, B, C, D, whatever you are using, those letters have to be converted into strings of 0 1s. And then you deliver that strings of 0 1 to the receiver, and the receiver will then automatically, or the way you have, let's say, coded this letters into strings of 0 1, suppose the receiver knows it, so the machine which is with the receiver, the machine knows it, and then machine is automatically decode it. And then if there is a chance of error, we'll find a way to rectify those errors, and then it will deliver the message. So the idea of Shannon was that whenever you have an information source, then you need to convert this to has to be converted, okay, into strings of 0 0 and okay, strings of 0 and 1, or which are called bits. Bits means binary digits. Okay, so binary digits. So B and IT bits. Okay, so binary digits, you can say. So this was the idea of Shannon. First of all, he wanted to define information in the context of digital communication system, and he said information is uncertainty, nothing but uncertainty. Now, what he meant by that, he meant if there is if there is something which is certain, it does not contain any information. And if you increase the level of uncertainty of that event, then of course the more information that will. So this is like an increasing function. Okay, the information is an increasing function of the probability. Like how much less it is, the probability is small, means it contains high information. Okay, higher information or a more amount of information. And then the next thing is information. Whenever you have some information source, you have that random variable, you have to digitalize this in order to send the information or the transmit the information. And he, in this paper, he proved two fundamental theorems, which will also, towards the end of this course, we'll try to prove this. First theorem was, so he proved two theorems. Whatever we are discussing now, we'll see all the examples and much more in details. But I'm just telling you the basic background of this thing, so you will have an idea what we are focusing in this particular course. So he proved two main theorems, okay, which made everything possible today. So first theorem is which is called source coding theorem. Source coding, and you should actually read about the life of Shannon. You will learn many things. Okay, and that also I should recommend you. Shannon is like, if you want to name mm, 10 mathematicians of the world, 10 people who have contributed greatly to the today's world. So Shannon will definitely be there due to this paper. So source coding theorem, and in this theorem, he first time used the word entropy, and he said entropy. He first introduces the word entropy, and he said entropy is a fundamental measure of information. Okay. So in the source coding theorem, so not theorem. Okay. So here he introduced the concept of what is called entropy. But I'll tell you another story about entropy. And introduce the entropy, let's say, as a fundamental measure, as a fundamental measure of information. Why I said a fundamental measure? Because later many people define variant of, this is what is called Shannon's entropy, a Shannon entropy. Many people define other kinds of entropy. Okay, that's why I said a fundamental measure. This is the first measure, you can say, of information. And here in this theorem, what he does is basically uh, uh, this this entropy, or this theorem, let's say, it will characterize the minimum rate of a source code representing an information source which is free of error. Okay, so we'll talk about this. So this is the first theorem, and the second theorem is called channel coding theorem. Channel coding theorem. This is also, I mean, this because of this, everything is possible. Communication is possible. This theorem. So as I said, that channel is what you can, informally speaking, channel is something through which you are transmitting the information. Or this 0 1s. Okay, you are sending. Let's say we have a satellite communication, some kind of a communication system where you are sending something to somebody. Okay, so that's what is the channel. And if you can create your own channel also, let's say some artificial channel you can create, so through which, like using some copper wire, you can create, right? So for example, I always say voting machine because it's a good example of a communication system. For example, you, or maybe in your laptop, whenever you type a, this a is displayed in your screen. So this is also a communication system. There is an input and there is an output also. Okay, and there is some bunch of things, some devices, some wires are there which can process the job, perform this job. So yeah, so the channel coding theorem says, like, you are always sending information through an unreliable channel, okay, some noisy channel, let's say. Okay, then he introduced a concept called capacity of a channel. He said how much information is possible through that noisy channel. Okay, he set a limit, and this is called, so he introduced this is called the capacity of the channel. So he set a limit for how much information you can reliably send through an unreliable channel, and he set a limit, and that limit is called capacity of the channel. So he introduced the concept of capacity of the channel, of a channel, let's say, of a noisy channel or unreliable channel. Okay, so we'll try to prove both the theorems towards the end of this course. We should see like what is the importance of these two theorems. By the way, I said that I'll tell you the story. There is another story about entropy, the word, because entropy is the main thing which we'll be discussing a lot of, most of the days during information. Actual story is this: entropy was already there in the literature. Okay, and he defined something. Okay, which we'll define later. He defined something in order to measure information. Okay, information or measure uncertainty of a random variable. Now he does not know how to call it, what it should be called. He has to give a name to it. Then there was a concept of entropy in physics. Okay, in fact, there was a concept of entropy in quantum science. Okay, in quantum mechanics. And there was a guy called von Neumann. Okay, von Neumann, who defined something called quantum entropy or entropy of something. Okay, in quantum mechanics. So he suggested one name, and so when he asked, when Shannon asked, what name should I give to this quantity? And von Neumann suggested him to call this entropy because of two reasons. The first reason is nobody understands what is entropy, and second thing is this is a fancy name. Okay, so nobody understands what entropy is, so it is a safe to call this as name. But anyway, so but there is a scientific reason why it should be called entropy. I mean, why it is, how it is related to the concept of entropy of a physical system. Okay, that also can be done. So because these are wise people, so that's why they said it like that, because nobody understands what an entropy is. So he suggested, okay, give that name entropy. That's how the word entropy came into the picture, or in the world of information theory. Yeah, so this is, I would say, the brief story of information, how information theory um, was developed in the initial days of 1948. So this is the story. And now what we'll have to do is we have to, so everything here, you now see, everything here is random variable, okay, and vectors are strings of 0 ones in random variable, and you want to quantify how much uncertain a random variable is, or a distributed probability mass function is, which is defined by some mm, random variable. Okay, yeah. So if you have any question, you can ask me now.
Sir, I have a doubt. Like we were saying, like if uh, if the probability is less, the thing contain more information, or the random variable contain more information.
Mm.
But what if the probability is zero? Then, like it is the least, but then it makes no sense because that thing will never happen. So how it is informative?
No. So there are two things. Okay, probability 0 does not mean that it will never happen. Okay, so yeah, so let me tell you this way. Okay, so this is where the bridge between discrete and continuous random variable. Okay, first of all, let me tell you that we'll discuss more about it. Okay, I just tell you that if something is more uncertain, then there is more information about it, because 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 of common sense, but we'll define why it is not. I mean, yeah. So because of common sense, meaning if something is uncertain, then it'll be more important. So information also can be thought of as amount of surprise, how much surprised you are. Okay. So if you're more surprised, that means there is more information. If you are not surprised at all, it means there is no information at all. Okay. And we'll always define the information or amount of this like if something has probability 0, we'll say that we'll not define entropy for that kind of a thing. I mean, we'll define what it is, okay, later on. I mean, probability 0 means there is an outcome, there is a possible outcome of this sample space, okay, which is in the sample space, which probability is 0. So for that, we'll not input that outcome, that probability, this which because it is 0, in the definition of entropy. We'll talk about it. But what I said is, suppose what I said is probability 0 does not mean that it is uncertain. It will not happen. Okay, so because this is what the difference between discrete and continuous. Suppose I give you a space on the wall. Okay, space on the wall. Now I give you a stick or maybe a stone, small stone or something. Okay, and then I ask you to throw that stone on that part of the wall. Okay, and then I give you a point inside that region, just one point, okay, inside the region, and I ask you what is the probability that you will hit that particular point using that stone. If you throw the stone, that stone will hit exactly at that point on the wall. Okay, what do you think? What is the probability?
0.
But you may accidentally hit as well. So can you define it as a 0? You may also hit that, right? How do you define that? Whether this is uncertain, like probability 0, does it mean it is uncertain, or it need not be uncertain?
So actually, like there will be the problem of this question lies in the hypothesis. If we think point as something which does not have any area, then it will be zero. But in this problem, if we are hitting with stone, then for sure stone will have some area.
Yeah, stone will have some area, but whether it will hit this point, what is the probability?
So the point that point, if we are if we are taking hypothesis as that point is having no area, then it will be zero. If the point has some area, then we can calculate the.
Now, how do yeah? So the question is, yeah, this is what the question. So what is the meaning of saying point has an area or point has area or not? What do you mean by this? What is the
So
area?
so what for that? Like first we have to define what is point.
Yeah. So what is point? I just
So
said point means I am marking one point there. Okay, that's what I say. Point means as a standard sense. I'm not going to mathematics, but you can define using mathematics also. I have no problem. Point means suppose once you hit the stone, this will hit at some particular point. You can mark it, and then you say, what is the probability now? Next time you will hit at that particular point. This is what a point is. Even if you
But sir,
suppose, yeah,
that definition is going against the idea, because if that is the case, then it does have a probability.
now,
The
so that is my question. So if it has a probability, what is that probability?
That probability can be defined on the basis of uh, wherever you hit, wherever the stone hits,
Uh,
uh, considering that the stone will hit over a
yeah, yeah.
certain area in the wall, then that will be considered, right?
Yeah, but what do you think? How many points does this region contain? Can you have a sum of all this? Like suppose some area, suppose some epsilon, some very
Yeah.
small amount. So how many points are there? Then you have to take a sum in order to conclude that the area that should be equal to the area. Like
Let's say the area
sum
is
over all the points.
epsilon, then
Uh,
epsilon divided by the area of the wall gives me the probability, right? So it is not, still not zero.
no, what I'm saying is, if that is the area, epsilon is the area of the point. How many points are there in that area? So uncountably, infinitely many points are there. So
Yes,
if you now,
infinitely.
yeah, if you now make a sum of epsilon uncountably many times, will that give you a finite value of that area?
No.
So why I'm asking this question? This is just to raise an idea. Like whatever we say or whatever we write, there is a difference because we are dealing with a physical world. Okay, so that's why you cannot see. Whenever I say that for every point, it means I'm thinking in terms of a discrete sample space. But this space is not discrete; it is continuous. I have to deal with it in a different way. So in that case, I will define some small areas of this finite number of small regions of the entire region, of the entire area. Okay, such that I can talk about integration, I can deal with this thing in a different way. Okay, so I will not deal this sample space as a discrete sample space. Instead, I'll define this as a continuous sample space. And then my definitions will be little different from whatever I do in the case of discrete sample space. So here, in the case of information theory, my information source is a random variable, but it is a discrete random variable. So we'll not have those kind of situations. We'll not have those kind of situations. Like, okay, we can have that kind of situation, but that cannot be interpreted in this particular context. So theoretically, we can have, but we will have some situation also, but that will not be considered as the Shannon's point of view here, whatever we are defining, let's say like a point-to-point discrete digital communication system, where our information source is always a discrete sample space. This is what we will study in this course. But if we want to do that in a continuous, so then we have to build some other machinery which will generalize his theory, Shannon's theory. That's a work of other mathematicians and computer scientists. We'll not discuss on that, but whenever we'll say probability zero, because we'll see how the entropy is defined. There we'll see probability zero means the what should be the information. Okay, suppose we have um, probability is zero. That means what? So how much information that does that's a thing contain? Okay, we'll talk about it whenever we'll have the formula. We'll see like if p is equal to zero for certain outcomes. That means we'll assume that using because it is discrete, so this is never going to happen. So that will not be a part of the definition of entropy. We'll not consider that. So we'll always consider because p, whenever p is not equal to zero or p is positive, the probability of those outcomes which are positive, for using those probabilities only, we will define the entropy. Okay?
Sir, I have a question.
Yeah.
Sir, can we think of entropy as, sorry, information as something which reduces the uncertainty? Uh, like, I was thinking you were giving an example of a message. So you were telling that, let's say that there are due to the noise factor in the communication system, so there arises some of the part of the message gets occluded or it gets distorted. So if we can say that information is anything which helps us to get the actual sense of the message, then it is basically something or the sample space which helps us uh, uh, like make sense out of the message. So I guess in certain way it is basically the reduction of uncertainty.
Yeah. So what we said, you just said, so if something is entropy, then you said something a complement of that as the entropy. So I think what we probably are trying to say is that sorry, my iPad got just a minute. Screen is off. So just mm, yeah. So yeah. So yeah, I think you said reduction of something. You said right, reduction of
I said reduction of uncertainty can be thought as information.
reduction. I mean, reduction means less uncertain means higher information. That is what I'm saying, or what is the
I
information?
My idea is that if I have a message
Mm-hmm.
and there is by some means that message is distorted. And by some means, so if that message is distorted, it contains some uncertainty. So
Mm-hmm.
if I can actually reduce that uncertainty, then that is information. So that is basically, let's say, a word is missing. So
Mm-hmm.
let's say I have a sample of words out of which that word can be there. So the information is basically the sample of words which can fit into the context to give it a proper meaning.
Yeah, but see, ultimately you have to quantify, right? I mean, how do you quantify that?
A reduction in uncertainty. Uh, uh,
Means suppose we have to give a value. Okay, how do you generate a value out of it?
okay, okay, I understand. Yeah.
Mm, yeah. So the thing idea is, I need a measure. It means I need to give a value because I need to. If I give you two different messages, then which one? Just like I said. So let's say I say tomorrow the sun will rise from east, or sun will rise from, let's say, west. Let's say I would say tomorrow it will be snowing in Calcutta. Okay, so now which one is more uncertain? So probably 100 years back there was snow in Calcutta, we don't know, or maybe 200 years. Okay, then we may have a guess. Okay, this is less uncertain or this is more uncertain than other things. So we need to have a comparison as well. So
Yes.
all, yeah. So we need to have a value, mm, for an event, or let's say for a context. Okay, to say that it is, whether how much information is there, I would say that that's much information. So in specifically in Shannon's idea was to measure it in terms of bits. So how many bits, so I'll tell you all these things later on. So how many bits you need to represent that information. So this, I mean, suppose I say this contains, this some random variable has 2 bits of information. That means what I'm trying to, so Shannon is trying to say is that whatever the random variable is, that can be written in terms of strings of zero ones, which can occupy 2 bits. So this is what it is. So yeah, so his unit is actually bits, or you can say other unit also like nats, other thing. We'll talk about it, but how many bits it is, kind of, we'll talk about it, because it is, I mean, in a physical class, from my hand expression you would be knowing, but here it is difficult. But what I'm trying to tell you is, oh, I didn't switch on the video also. Okay, so here what I'm trying to tell you is, like uh, what do I say, so what I was telling, uh, what I was saying, I forgot. So mm, what I was saying. So
So you were
Shannon's.
telling about bits and information.
Oh, okay. So yeah, so the question is, for example, it is kind of, what I would say. Let's say you have some letters, okay? Suppose, or some alphabets using which you are writing a message, okay? Now for each letter, so his idea is, Shannon's idea is, whenever you have this information source, you have to digitalize it. That means for each letter, let's say, or each alphabet, you have to define a string of zero ones, and it will have a length. So for each letter, you'll have a string of zero ones. And based on the distribution of the letters, distribution means how many times which will frequently occur or not, depending on that, because these letters will come with a probability, because this is what the definition is. The information source means it is a random variable. So everything will come with all possible outcomes will have a probability value. So probability of A, probability of B, probability of C, and so on. So whatever be the probabilities, okay. So what I will do is, in fact, entropy means, I'll show you mathematically what it means, but I'm just explaining it. Entropy means, so you have, let's say, small length, bigger length, small length, bigger length, medium length, whatever it is. What is the average length, okay, of all possible letters? So this is what it is going to be called the entropy actually. So it is the expected value, okay, in order to write one of these letters. Okay, this is what will be mathematically or maybe in the sense of real coding. One can say what is entropy. So it will be the average value to code a particular letter in terms of a sequence. So the average length of all these strings of letters, strings of zero ones, binary strings, the average length will be actually the entropy. But we'll see it. I mean, how will oh my iPad. So we'll see. I mean, how it can be defined this entropy. Yeah. So this is again. So we'll see that. Yeah. Anything else you want to? Okay. So yeah. Now, since we already have known that mm, probability and other things will define random variable, and these things will define what is an information source, which is the main part of this. So let us uh, formally recall some of the basic definitions, and using which we will gradually develop the concept of entropy, or how to measure information of a random variable, or of an information source. Okay. So first of all, so I think I said what a probability space is, but in the context of information theory, most of the time we call it ensemble. Okay. So what is an ensemble? It is okay. Ensemble meaning. Uh, do you know what is the meaning of ensemble? Ensemble. So you have certain possibilities, and sum of the probabilities is equal to 1. So possibilities means sum of the possible outcomes, and for each outcome we have a probability. So and sum of this probability is equal to 1. So this is what is called an ensemble. Ensemble means this. Then the sample space, the set of possible outcomes, is the ensemble. Okay. So it is what is called the probability space in our standard undergraduate class. So ensemble is which is associated with a sample space, and a probability measure. Probability measure. So this is what is called an ensemble, and we'll always denote this ensemble. So okay, let me just add it for the sake of this. This is equivalent to probability space, because this is how probability space. By probability space, so what do you mean? That there is a sample space, omega or s, whatever you know, and then there is a set of events, whatever it is, and there is a probability measure, which is p. So p is a function from, let's say, a to 0 on. Okay, satisfying. So using the axiomatic definition of this, probability of anything should be bigger equal to, or equal to say a, and bigger equal to 0 for any a is in this. This is the axiomatic definition of probability. And what do you say? P of omega is equal to 1. And another condition is if we have disjoint mutually exclusive events. So if a1 dot 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 ak are mutually exclusive, means disjoint, because event is a subset of the sample space. Exclusive, then their union will also be an event. I have to go to the next. Otherwise, I can just write it. P of A1 union dot 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 union AK is equal to sum of P A I equal to 1 to K. 1 to K. Yeah, so this is port. So here you can see like this is what an ensemble is. This is what we define or an. Okay. Now, so yeah, so let's say instead of writing this entire probability space, if I just write let U be an ensemble, then it means that U is that um, probability space, or U denotes that probability space. Ensemble, let's say with sample space, let's say A1, A2, dot 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 AK. Okay, and let's say P of U A something AI. Okay, so whenever I write this, so that means it is U is the ensemble here, and P is the probability, and P is defined for an outcome, possible outcome, which is AI. Okay, or you can simply write, yeah. So this kind of notation will be used. I'll be using this kind of notation. Okay. What else? Now I may have, instead of one ensemble, I can have two different ensembles. Okay. So let's say I have what? Uh, okay. So let I have two different experiments, and A1, A2, AK, and say B1, B2 something, B1, B2, BJ. Okay, these are our sample spaces. Sample spaces corresponding to two experiments. Okay, and then we can talk about uh, joint experiment, or it's a joint space. Okay, so I'm not giving you an example because I think you know, I'm just repeating this thing. So let's say this represent the ensemble U. Oh, U also denoted like union. So let us, it looks like union. So let's say this is the ensemble X, and this is the corresponds to the ensemble Y. Then we can define PXY kind of a thing, which is a joint space now. And here we can say joint space means it's like AI BJ kind of a thing. AI BJ. What is the probability of this? So once this is defined, so this is a joint space. So we can call this joint ensemble. XY is a joint ensemble. Now, once we have this, um, or sometimes we call it joint probability space. So, yeah. For example, I mean, if you have, if you want to give an example, in the real context of information, okay, so you can say this is the input, okay, the information source. There is a random variable, and the output for the receiver's end, okay, the receiver will also receive a random variable. So let's say these are the letters which you are sending. Just let us assume that you are sending each letter, okay, some alphabets you are sending. then this guy, the receiver, will also receive some alphabets, okay, because we're sending that. Then the question is, suppose you send A 2 times, so receiver must also get A 2 times, right? So then we can compare these two random variables. One is input random variable, one is output random variable. So X, in the context of information system, X could be the input random variable and Y could be the output random variable. Okay. Or in a general, like in probability statistics, I will not take examples from probability statistics class, but let me just take for this case. It is like you are measuring height and weight of a person. Okay, so height is a random variable and weight is a random variable. So then what is the probability of this height, that weight, and so on? So typically when we have this finite, let's say we call this as x and this as y. So if these are a1, a2, this dot dot dot, these are b1, b2 dot dot dot, then we define probability of ai, bj, and so on. And this is how it is defined. Yeah. So how it is defined. Then what we, in a standard practice, what we do is, suppose we want to define what is the probability of, let's say, ai. Okay, so you are in a joint space x and y, a joint ensemble, and you want to just define what is the probability of ai. Okay, by the way, so this a, let's say it is in just x. Okay, so the joint distribution is given to you. Now from there you want to find out the marginal distribution. This is what is called the marginal distribution. So how do you do that? So this will be sum of probability of xy and ai, and whatever you want to write, some bj, and j is equal to 1 to up to whatever number, 1 to up to some j, whatever the number of outcomes we have, b1, b2, let's say bj, capital J. So this is how what is called the marginal distribution sometimes. Marginal distribution, a marginal probability distribution. Okay, so from the joint you can define marginal same way. So without going into all this complicacy, most of the time I will write like this, that probability of some x, okay, or sometimes we can write x equal capital X equal to small x is equal to sum of this pxy. This is for all y. That's it. Okay, so this will be my standard notation. But since first time I'm writing, so, and similarly you can write what is py, let's say. So you can write over all x p of xy. So this is the marginal distribution of y from this joint distribution of this. And then we can define what is called the conditional probability. So let's recall what is the definition of conditional probability. So suppose we have two random variables or two ensembles, x and y. Then how do you define, let's say, p, whatever, x, y, whatever, something is given and something you want to know. For example, in the context of information theory, in a digital information system, you are sending some x. This is the sender, and here is in the right hand there is a receiver. Now suppose you receive some particular symbol, let's say y. This you know. Then the question is, what is the probability? Because there is a noise in the channel. Okay, I'll give you examples of the channel whenever it will come in the context. Since there is a noise in the channel, you are the sender probably is sending x, but the receiver may receive y due to the noise. Okay, receiver y. Then the question will be, if the receiver receives y, what is the probability that the sender actually sent x and y is received? So that's why you need to use the concept of conditional probability. Or maybe the sender send x, which you know. Then the question is, what is the probability that the receiver will receive some y's, some alphabet y? Y could be equal to x as well, but what is the probability that this receiver will receive y when you already know that the sender sent the alphabet X. Okay, so that's why we need to understand the notion of conditional probability as well. So let's say, yeah, so y given x, and then I can write it like whatever you want to write. Like let's have some bj. Let's say is given, ak is given, and you want to find, so x is given, y. Okay, so this will be y. How to define conditional probability? It is probability of xy the joint bj ak defined by divided by probability of corresponding to x ak. Of course, this should be not equal to 0 when px ak is not equal to 0. Okay, so this is what is conditional probability. So in general, I can also just write. So for the first time I'm writing this, otherwise I can just write py given x is equal to pxy by px. That's it. Okay, that's it. Yeah. Similarly, if y is given x, also you can write. So yeah, this you can write. But these are all random variables. Then we can talk about our pair of random variables, let's say x and y. But we can talk about tuples of random variables as well. Let's say x1, x2 dot xk or xn be a sequence of random variable. So basically what is happening is, sometimes what happens is you say something to somebody, then this guy say something to somebody. So there are different channels, okay, which are simultaneously connected. So this is the first channel, then connect to the second channel. So output of the first channel is the input for the second channel. Then output of the second channel is the input for the third channel, and so on. Okay, so there can be multiple number of random variables. Okay, and then we can call it a random vector. Then the question will be, how do we define random vectors and probability concepts? How are they defined? So this is just the extension of a pair of random variables to tuples of random variables or a random vector. Yeah, I think we should stop here today. And we'll meet next day, let's say Saturday, 10 to 12. We'll meet again. So if you have any other question, you can ask me. Let me stop.